Howdy guys, we want to start our thermochemistry unit and see if we can try to blow something up. First we have to understand what energy is. It's the capacity to do work or to produce heat. Now the first law of thermodynamics states that energy cannot be created or destroyed. It has to be converted from one thing to another. We'll explain more about this later in nuclear chemistry. That's going to be fun. Now we need to review a couple things about when you learned in middle school. You learned about potential energy, which is the energy due to the position or the composition, kind of like chemical bonds or at the top of a roller coaster, or a rubber band, something like that. Now, kinetic energy is the energy of motion right here. So motion is the key point. Now, it depends on the mass and the velocity of that object, right? So a heavier object will have a higher kinetic energy, and a faster object will also have a higher kinetic energy. So the girl dropping the ball on the hill, this ball has no kinetic energy because it has no velocity, but as she drops it, it gains velocity, so it gains kinetic energy. It also loses potential energy. So the potential energy is converted into kinetic energy. So that's just the important key thing to learn. Now, getting you ready for physics, the official formula for kinetic energy is mass, 1/2 mass times velocity squared. Now, mass is in kilograms, velocities in meters per second. And so if we put those all together, we get joules, okay? So joules is what we're looking for. That's going to be our key unit of energy. Now, there are 6 forms of energy. 3 for potential, 3 for kinetic. So for potential energy, we have chemical energy, stored mechanical energy, which would be like a rubber band. And then nuclear energy is the energy that is locked in the actual nucleus. That is the strongest force in the world, in the entire universe. And the energy holding those protons together, remember, those protons are all positively charged. They hate each other. They don't want to be next to each other, but they still are because they're held together by that energy, that nuclear energy. Now, the kinetic energy is thermal energy, electrical energy, mechanical energy. You probably heard of those before. So chemical energy comes from a lot of different places. It comes from coal. We dig it up out of the ground. We can burn it, used to power our power plants, because that coal was used to heat up water to turn it into steam. That steam turns a turbine, which turns it into electrical energy, which the electricity gets pumped into your house. We have food energy over here. That's what we eat to survive. We have some natural gas being burned, right? So that comes from the earth. We also have batteries. That chemical energy from one element into another. There's an electromotive force. There's a force driven by electrons from one metal to the next. So that is going to be our energy there, or in gasoline, something like that. Take my IB class and you will learn all about this. Now, thermal energy is also where we want to look. Now, there's 3 different types of that one. That's the radiation. That comes from like the light of an electric stove. You see how it heats up. It turns red. You can also feel the heat coming off of it. That's radiation. The convection is symbolized by the arrows right here with this turning, the swirling of the arrows. The hot water rises and the cool air descends, just like that. And then the conduction is the heat that's traveled from when you actually physically contact another object, like your hand, onto the handle. Now, this is the most effective. This is the least effective right here, or least effective method of heat transfer. So let's start talking about heat transfer. Well, first, think about a sparkler. A sparkler emits particles of metals that have temperatures of up to 3,000 degrees Celsius. So this is like, thermite, extremely hot reaction. However, the sparks don't burn you if they land on you. Why not? Okay. Well, the answer has to do with heat versus temperature. Those sparks don't have very much mass, so they don't have very much heat. They are very high temperature, but they have very little heat. So temperature is defined as the measure of average kinetic energies. Now notice I said average kinetic energy of the particles. Now measured in Celsius or Kelvin. All right. And it's basically the motion of the molecules. Now we have 400 Kelvin here, so the arrows are longer, which symbolizes that they're moving faster. At 50 Kelvin, they are moving slower. We have smaller arrows. Now for heat, that is the sum of the total kinetic energies. So if we added all the kinetic energies together, we would get a much higher total. Think about if I added all of your daily grades together versus if I took the average of all your daily grades. Which number would be higher, right? I would add all your daily grades together. That would be higher. So heat is, something different. It is mostly involving the transfer of energy between two objects, okay, due to a temperature difference, okay? Now, this one is measured in joules. Now, temperature was measured in Celsius or Kelvin, right? So it always flows from high energy to low energy, right? So from hot to cold, right? Just like Robert De Niro is in the movie Heat, right? Hope you get that. High temperature to low temperature. So let's think about this. Which one has a greater temperature? 1,000 grams of water at 25 degrees Celsius or 1,000 grams of water at 45 degrees Celsius? Well, it's going to be 45 degrees Celsius, duh, because it has a higher temperature, right? Well, which one has a greater heat content? The 1,000 grams or the 100 grams? Well, that's going to be the 1,000 grams because the more mass something has, the more heat it is going to have. All right, we'll get into another formula in the next video. Which sample has molecules with the greatest average kinetic energy? That is going to be this guy right here. 1,000 grams of H2O at 45 degrees Celsius. That has the highest amount of mass and it also has the highest temperature. Now, which sample has the greatest total energy? Now, 1,000 grams or 100 grams? Well, that's going to be the 1,000 grams because we're looking for the total energy. That's also another name for the sum of the energies, which is the heat, right? So this one has the highest heat. Very good, because that's the highest mass. So, which has more heat? A pipette full of water at 100 degrees Celsius or a beaker full of water at 80 degrees Celsius? Well, we're going to say the beaker because the beaker has many times more mass, and which makes the difference in the temperature rather insignificant. Okay. So now let's look into this method of heat transfer. Now, to do this, we have to understand a couple of other vocabulary words. We have to understand that our reaction is known as the system, and whatever is outside our reaction is known as the surroundings. So when I say system, I'm talking about the reaction, and the surroundings is everything else. Okay? So if heat flows into the system, it is going to be an endothermic reaction. If heat flows out of the system, then it is going to be exothermic, right here. So an exothermic reaction, which is something that releases heat, energy flows out of the system, the potential energy is changed into thermal energy, and the products will have a lower potential energy than the reactants, okay? Products have a lower potential energy than the reactants. So, if you have a chemical equation, the heat term is always written on the right side because that is saying that heat is coming out. Now, if it is written off to the side, it always has a negative sign. Just remember that. We'll explain more about it later. Now, for an exothermic reaction, the reactants in a graph form, it starts with the reactants are over here and the products are over here, and you really just need to know these two positions. Don't worry about the hump in the middle right now. So we just need to know that the products have less energy than the reactants. That's because heat came out of the system, all right? And so the products have less heat, or they have less energy. Now, an endothermic reaction is just the opposite, right? Energy flows into the system, thermal energy is changed into potential energy, so the products will actually have a higher potential energy than the reactants. This time, the energy term is going to be on the left side of the equation, and the enthalpy sign, the delta H sign, is going to have a positive right here, all right? So, and the graph will look like this. The products will have more energy than the reactants, and just know about those two positions right there.